Hello everyone, welcome to my channel. In this video we'll be learning how to calculate internal energy of the beam system and the vertical deflection at point C. Okay, please don't forget to like, comment and subscribe to stay updated for more civil engineering tutorials. Now let's deal our problem. Our problem is to determine the internal energy and the vertical deflection at point C. So this is a beam system. In order to calculate the internal energy and the deflection at point C, the first step is to draw the free body diagram so as to obtain the reaction, the support reaction at support A and B. So let's draw its free body diagram of this beam system. This is pin support, so it is affected by two support reaction. It will be vertical reaction, let's say RA, and the horizontal reaction at point A. This will be horizontal HA. This is roller support. It is affected by only one reaction, which is vertical reaction. Let's say RB, vertical reaction at point B. Here there was 10 kilonewton per meter uniform distributed load. Okay, this is free body diagram. So let's calculate the support reaction by taking the summation of. In order to obtain this support reaction, let's take summation of moment at point A is equal to 0. Summation of moment at point A is equal to 0. All local direction will be positive and local direction will be negative. Now, since we have taken summation of moment at this point is equal to 0, HA and RI will be equal to 0. Now, RB, it will rotate towards point A, so it will move in anti-clockwise direction, so it will be negative. RB, in order to obtain moment at this point, RB times its distance, so it will be 10 RB. Okay, plus this force, it will move towards point A, so it will move in clockwise direction. It will move in this direction. So it will be 10 times 10, so as to obtain force times its perpendicular distance from this point to this point, which is 10 over 2. 10 times 5 plus 5 moves clockwise in clockwise direction. Force times perpendicular distance. Perpendicular distance of this force is 15. So it will be 5 times 15 is equal to 0. Therefore, 10 RB is equal to plus over 10. It will be this one. So in order to obtain RB, will be divided by 10 every side. It remains 57.5 kilonewton. So in order to obtain a vertical RI, we take summation of vertical force is equal to 0. Positive, upward and downward, it will be negative. So upward you having RI plus RB, this one, minus downward force. is 10 times 10. This is 10 kilonewton per meter. You want to obtain point load at this, it will be 10 times its distance. So 10 times 10 minus 5 is equal to 0. So Ra plus Rb, it will be 105 kilonewton. So Rb we have calculated, which is 57.5 kilonewton. So Ra it will be 105 minus 57.5. Ra it will be 47.5 kilonewton. This is vertical reaction for point A and point B. Now, let's consider horizontal reaction. Horizontal reaction is equal to 0, so as to obtain HA. So since there is no another horizontal reaction, so HA will be equal to 0. Therefore, HA is equal to 0 kilonewton. After obtaining this vertical reaction, now in order to obtain internal energy, total internal energy vertical reaction, we know that internal energy, total internal energy is equal to moment due to applied load times moment due to applied load over 2EI from 0 to a certain distance dx. So in order to obtain this internal moment, we'll cut a section. We know when we cut any member, we cut a section at a certain point, internal forces are produced. Internal forces are normal force, shear force, and the bending moment. Internal moment means. So in order to obtain, for this beam system, we'll cut section at 2 points, at this region and at this region. So it will be in this way. It will be in this way. This is Ra. Ra was 47.5 kilonewton. Rb was 7.5 kilonewton. Here was 5 kilonewton. 5 kilonewton. This was one uniform distributed load, 10 kilonewton per meter. From here was 10 meter, 5 meter, 5 meter. So in order to obtain internal moment, we will cut section at this point, let's say section 1, and at this point, let's say section 2. Now, let's consider section 1. Section 1. Section 1, it will be in this way. This is uniform distributed load. Here was Ra, kilonewton. This is vertical reaction. These are internal forces. Normal force at x at a known distance x. This is a known distance x. Okay, this is internal moment due to applied load at distance x. So let's say moment due to applied load at point x. This was 10 kilonewton per meter. So in order to obtain the moment at this point, we take summation of moment at point x is equal to 0. Clockwise direction positive and clockwise direction will be negative. So this moment, it is in clockwise direction, so it will be positive. So it will be mx minus plus this one plus force times perpendicular distance, it moves in clockwise direction to this point. So it will be 47.5 x, okay, minus this one, since it is moves in anti-clockwise direction. Force times, now to obtain forces at this point will be 10 times x, will obtain point load at this point, times perpendicular distance. Perpendicular distance is x over 2. So it will be 10x times x over 2 is equal to 0. Now, moment due to applied load at point x, it will be, this is 5x squared, it will be 5x squared minus 47.5x. Now, so what the internal energy for this section 1, it will be from 0 to L to M, moment due to applied load times moment due to applied load over 2 EI dx. Therefore, internal energy for this section 1, it will be from 0, its distance is from this point up to this point, so its distance is 10. So it is from 0 to 10 meter. Moment due to applied load we have obtained here is 5x squared minus 47.5x times 5x squared minus 47.x over 2 EI. When you multiply this one, it will be from 0 to 10, it will be 25x power 4 minus 470.475x power cube plus square of this one plus 2256.25x square over 2 EI dx. Now let's integrate this one. This is constant. Let's factor out. When integrate this one, it will be 25x power 5 over 5 minus 475x power 4 over 4 plus 2256.25x power 3 over 3, integral from 0 to 10. Now, 5 power 5 minus 475 power 4 plus 2256.25 power 3 over 3 10 divided by 2. So our answer, it will be 96875 over 3 EI, as this is internal energy for section 1. Now let's consider section 2. Section 2. Section 2. Section 2. Section 2. Section 2. To obtain section 2, you may take this region from this point to this point, or you may take this section to the left side of the beam after cutting section 2. For now, let's consider section at right side. So this one Here is 5 kilonewton. Here it will be shear force Vx, moment due to applied at point X. This is a known distance. We have cut in a section. This is normal axis. Normal force at point X. Okay. In order to obtain this moment, we take summation of moment at X is equal to 0. Clockwise direction positive and clockwise direction negative. So this one, it moves in anti-clockwise direction, so it will be negative mx. This is moves in clockwise direction, so it will be plus 5 times x is equal to 0. So mx is equal to 5x. So internal energy for section 2, it will be from 0 to L, moment due to applied load times moment due to applied load for section 2 over 2 EI dx. Moment due to applied load is 5x squared, so integral from 0 to 5. We take the distance. We take the distance from this point to this point. That's why we take it from 0 to 5. So it will be integral 5x squared. Moment due to applied load is 5x times 5x over 2EI dx. Internal energy it will be this is constant left. Let's factor out from 0 to 5. 25x squared dx. Let's integrate this one to EI. This will be 25x cubed over 3 from 0 to 5. 25 calculate 25 divided by 2. It will be 3125 over 6 EI. So in order to obtain total internal energy of that beam system, total internal energy of the beam system will take total internal for section 1 plus total internal energy for section 2. So total internal energy it will be for section 1 was this one. Or this one was 96875 over 3 EI plus for section 2 was 3125 over 6 EI. Therefore, total internal energy it will be plus 96875 over 3. Our product will be 65625 over 2 EI. Therefore, this is the total internal energy. Total internal energy of the beam system is 65625 over 2 EI joule. Okay. The next step is to calculate the deflection at point C. Deflection at point C. Deflection at this point. In order to obtain, we know that deflection is obtained by this formula. Deflection. Deflection is obtained by this formula. Integral from 0 to a certain distance. Moment due to applied load times moment due to internal moment due to unit load over EI dx. Moment due to applied load for section 1.1 and section 2.2.2 we have obtained. So in order to obtain deflection for point C, we are required to calculate the moment due to unit load. So the moment due to unit load is obtained by removing all of the applied load, this one, and introduce unit moment at point C, at this point. Now, let's say remove, in order to obtain moment due to unit load, remove all applied loads and introduce unit load at point C. In order to obtain moment due to unit load. Now, our beam system, it will be in this way. It will be reaction at point A, horizontal reaction at A. Here it will be reaction at point B. This is point C, point A, point B, point C. We have removed all applied loads, uniform distributed load which was at this region, and point load which at this region, and we have introduced unit load at point C, which is this one, unit load. Now, in order to obtain moment due to unit load, the first procedure is to calculate this vertical reaction. This vertical reaction RA, RB, and horizontal reaction HA. So, in order to obtain this support reaction, let's take summation of moment at point A is equal to 0. Clockwise direction will be positive, and clockwise direction will be negative. So, from this point to this point is 10 meter, 5 meter. Moment at this point is 0. So in order to obtain moment at this point, it will be this, it moves in anti-clockwise direction. So it will be negative 10 RB plus this load moves in clockwise direction towards point A. So it moves in this way, clockwise direction. So it will be 1 times perpendicular distance from this point to this point, which is 15, is equal to 0. Therefore, 10 RB is equal to 15. Therefore, RB, it will be 1.5 kilonewton. Okay, let's proceed. In order to obtain vertical reaction, to obtain a line, we take vertical reaction is equal to 0. Upward, positive, and downward, negative. So, Li plus RB, this moves the upward is positive, minus 1 is equal to 0. Therefore, Li it will be 1 minus RB minus 1.5. Li it will be negative 0.5 kilonewton. So, in order to obtain moment due to unit load, we cut section. At this region, section 1.1 and section 2.2. Now, let's consider section 1.1. Section 1.1. So we cut section this one. This is section 1.1, section 2.2. Let's consider section 1.1. section 1, so it will be in this way. Ally we have obtained, which is negative 0.5. This is shear force, normal force. This is moment due to unit load at x. As this is a known distance x, we have cut a section. So we take summation of moment at x is equal to 0. So positive direction and clockwise negative. This moves in clockwise direction, so it will be positive. So mx plus this also ally moves in clockwise direction. Since it is negative, so it will be negative 0.5 x is equal to 0. So we have moment at this point, it will be 0.5 x. Now deflection for section 1, it will be from 0 to 10. Moment due to applied load for section 1 times moment due to unit load for section 1 over EI dx. Moment due to applied load for section 1 was this one. Was integral from 0 to 10, 5 x square minus 47.5 x times moment due to unit load is this one, 0.5 x over EI dx. So deflection for section 1 it will be 0 to 5. When you multiply this one, it will be 2.5 x cube minus 23.75 x square over EI dx. Now let's integrate this one. When you integrate this one, it will be 2.5 x power 4 over 4 EI minus 23.75 x power 3 over 3 EI. Integral from 0 to 10. Therefore, deflection for this point, it will be 2.5 minus 23. Between 10, it will be negative 5,000 over 3 EI. This is meter. Since it's deflection. Now for section 2 this one. Section 2 consider section 2 Section 2 Section 2 it will be in this way. This is 1 unit load here. This is shear force Vx, normal force at point x. This is unit moment at point x. This is a known distance. Now in order to obtain, we take summation of a moment at point x is equal to 0. Clockwise direction positive and clockwise direction negative. So it will be, this moves in anti-clockwise direction, so it will be negative mx. Is this unit load moves clockwise direction towards towards this point. So it will be plus 1 times its perpendicular distance is x, so it will be 1 times x is equal to 0. Moment due to unit load for this point, it will be x. Now deflection for section 2, it will be from 0 to its distance from 0 to 5, its distance 5, so we integrate from 0 to 5. Moment due to applied load times moment due to unit load for section 2 over EI dx, 0 to 5. Moment due to applied load for section 2 moment due to applied load for section 2 was 5x, was 5x, this one was 5x times moment due to unit load for section 2 this one is x over EI dx. When we integrate this one, it will be 5x cubed over 3 EI. Integrate from 0 to 5. Now deflection for section 2 5 it will be 625 over 3 EI. This is meter. Now we are going to calculate deflection for point C. Deflection for this point. In order to obtain deflection for point C, deflection for point C, we will take deflection which we have obtained for section 1 plus deflection which we have obtained for section 2. Now, deflection of point C is equal to deflection of point 1 was negative 5,000 over 3 EI plus 625 over 3 EI. We will obtain is equal to negative 4375 over 3 EI meter. Therefore, deflection at point C is equal to negative 4375 over 3 EI meter. Now, this is our final answer. Thank you for watching this video. Please don't forget to like, comment and subscribe to stay updated for more civil engineering tutorials.